Again, the scenario is this. I have a spring. It's at its equilibrium length. And I attach from here a mass. That mass oscillates down and then back up over and over and over again. So our assignment was to describe the motion of the object in terms of energy. So I want to talk about the energy and how it transferred between things, and I'm using motion to help me do that. So what is the velocity of this object when it's at the top of its oscillation?
0.
0. What is the velocity when it's at the bottom of its oscillation?
0.
0. And where is it at its maximum? Somewhere in the middle, right? So whatever's happening with kinetic energy whatever's happening with velocity must also be what's happening with kinetic energy. Because kinetic energy, as we're going to say in our notes, is just the motion or the energy for an object in motion. So if it's in motion, it has kinetic energy. If it's not, it doesn't. Now, thinking about the other things that are happening, what type of energy do I have at the top here? Again, we stated that our ground level, our 0, was going to be this bottom spot right here. So what kind of energy did I have at the top? Gravitational potential. Why don't I have any spring energy up here? Because why? The spring's at equilibrium, so it hasn't been stretched or compressed. What about all the way at the bottom? Now I don't have gravitational potential because I'm at the bottom. We called that 0. Yay. But I do have, what? Spring potential energy. Spring potential energy. So if I wanted to describe this in terms of motion, I can say this. Going from top to this middle to the bottom, I'm turning GPE into two things. As I go towards the middle, what two types of energy am I turning GPE into? Kinetic, because it's starting to move. And which one? Spring potential, because I'm stretching the spring. Then, as I head to the bottom, right, I'm going to continue turning GPE into spring potential. And now I'm also turning all of the kinetic energy I had into spring potential as well. So that is how I would describe the motion using energy. As I drop from the top position, I turn gravitational potential into both kinetic and spring potential, so I speed up. Once I get to that middle, I'm at Vmax. Now my kinetic energy is also going to start turning into spring potential energy. So all of my kinetic energy is going to go away and turn into spring potential. The remaining gravitational potential energy will also turn into spring potential energy. Okay? Questions about this one? The other one's slightly more complicated. Really, there's only a top and a bottom. Because in this scenario, I just lowered it down. So I talked about this. All that happened here was that I turned gravitational potential into spring potential and kinetic, but what happened to the kinetic energy? I let it go out of velocity, but what happened to the kinetic energy? By who? This was taken out by negative work. I did negative work to the object and took that kinetic energy out. So at the bottom, you only had some spring potential energy from, obviously, the spring being stretched. But the bottom, that mass was not moving, right? This is the scenario where I just lowered a mass and got it to the bottom. So in this scenario, energy, total mechanical energy, was not conserved because I did work to it, took energy out of the system. And that's the difference between these two scenarios. All right, let's try and do what we said we were going to do last class. Did we finish by any chance that graph over time? Yeah. We did? Okay, so we don't need to do that again. Okay. All right, then let's start talking about conservation of energy. Oh, or drop an eraser. Those are both options. We could have done either thing. Opted for dropping. Okay, don't need all of those. Let's talk about conservation of energy. All right. First rule, energy is conserved. Yay! Energy is conserved. Energy can neither be created or destroyed. It is conserved. At the very least, if you want to talk about the really great big physics of it, we can talk about the universe-sized physics of energy being conserved anytime you want. We can have a conversation about that. But at least in the terms of our AP Physics C classroom, on any context, any situation that they give you, obviously energy is going to be conserved on the whole. All right? If you have watched some Veracity video and been suggested, otherwise you and I can have a conversation some other time about that. But for today and in my classroom, energy is conserved. All right? Now, in a situation, total mechanical energy, that's what that is, total mechanical, I'm not going to forget how to spell things, energy, is conserved unless what? What has to happen for total mechanical energy to no longer be conserved in a scenario here? A dissipative force, we could just call it any outside work, right? I guess I technically, in our example scenario where I lowered the mass slowly, I was a dissipative force. But we're just going to say unless an outside force does work to the system. So, before we talk about the three types of energy in more detail, the three types that we mostly care about, the three types that really AP Physics C constrains us to, inside of a system at least. Let's talk about this example and make sure we understand it. So I'm going to start with a box on the ground. So if I just have a box all by itself on the ground and my system is only made of that box, okay? And I push the box, okay? We're going to assume there's no friction. I push the box. I walk over to the box and I push it, okay? What has happened to the total mechanical energy of this box system? I pushed the box. I'm not part of the system. The box is the system. What has happened to the box? What was its initial kinetic energy? Zero. What's its current kinetic energy? More than zero, right? So what happened to the total mechanical energy? Did it increase, decrease, or stay the same? It increased. So when total mechanical energy increased, that means that's because I did positive work to the system. So I added positive work to the system. That's how total mechanical energy increased. Okay? That's how that worked. So if I push the box and it starts sliding, right? If the box is the system by itself, then I was an external force. So I did work to the system. So in this case, energy is not conserved. That's what we're talking about right now. We're trying to understand the scenarios and the systems where energy would be conserved and where it wouldn't be. So let's do this again. So this is me pushing a box. If I'm not a part of the system, if the box is the system by itself, the only energy it can have is kinetic. It started with no kinetic energy and ended with some kinetic energy. So therefore, its total mechanical energy increased and the work increased with it. Okay? Let's do another example. I'm still leaving only the box. Only the box in my system. So I now lifted the box and put it on a shelf. So that's the final position of the box. I lifted it up and put it on a shelf. I did that. I lifted it up and put it on a shelf. It's now resting at the top of this shelf. So let's start with total mechanical energy. Was it conserved or did it increase or decrease?
Increase.
Why?
Because you picked it up.
So what energy increased?
Gravitational potential.
I don't have gravitational potential because Earth is not a part of this system. That's important. So if you don't think about that all the time, make sure you make a reminder in your notebook. If Earth isn't a part of the system, it counts as an outside force. And I can't have gravitational potential energy. So since the box is the only thing in the system still, my total mechanical energy can only be kinetic. So what happened to the kinetic energy of the box when it got to the top? It's still 0, right? So total mechanical energy is unchanged. So what happened? Well, I'll tell you what happened. I did positive work to the box. That's me. I did positive work to the box. I lifted it up. What did negative work to the box? Earth. Earth did negative work to the box. We're going to talk about work more next class, but as a reminder, work is dependent on which direction the force is going. So, and then which direction the distance it was displaced is. So, when I lifted the box, I did a positive force in a positive direction. I did positive work. Earth, its force was downward, but the object went upward, so that's a negative work force, positive direction, negative work. So, those two works equaled out. I put the box on the shelf. It's up there. Its total mechanical energy hasn't changed. What I'm doing right now is showing you scenarios that's not how you normally think of these things, to show you that it really matters what's in my system. Okay? So if I just slightly change this scenario and say now the Earth is a part of my system, what happened now? If Earth is now a part of my system, what happened to total mechanical energy? It increased, right? Total mechanical energy increased because now I have some gravitational potential. This doesn't count anymore because it was the Earth's work. The Earth can't do work because now it's inside of the system. So the only external force that did things on the system was me. I did positive work to the system. That's how the total mechanical energy increased. So this would be really important for a conceptual question. If I don't read the question correctly and know whether it's a box Earth system or just a box system, and the question is what happened to the total mechanical energy, the answers are vastly different. So I've got to be paying attention to what they say the system is. Last example, we'll go back to me pushing the box. I'm going to push the box. Earth is still a part of my system, but now, me, Miss Limer, I am also a part of the system. I am now a part of the system as well. Well, I've entered the system. So, I'm again going to push the box. Again, I'm saying that I'm standing right here and not moving. I'm going to push the box. So, talk to me about total mechanical energy this time. What is the total mechanical energy of the Miss Limer box Earth system? Conserved, increased, or decreased?
Wait, if you push it?
I pushed it, but I'm now part of the system.
Oh, wait, I thought you are.
Yeah, I'm part of the system.
Yeah.
Yeah.
So you pushed it.
I pushed it.
But now you're part of the system.
But now I'm part of the system. Yeah. So what happens to total mechanical energy? It's the same. It did not change. So what transfer of energy happened, right? The box was sitting there. We know the box by itself now has some kinetic energy. Where did it come from? Inside of the system. Inside of the system, that energy was transferred from one place to another. So where did the box's kinetic energy come from? Inside of the system.
Potential energy in you.
Yes, exactly. My potential energy. We'll call it mechanical for today. It's probably actually the lunch that I had that pushed the box, right? That's perfectly fine. So is chemical. We'll just take a swipe on that. The reason I can call it mechanical is because I have muscles, they compress and stretch, acting like springs, so I can call it spring potential energy inside my body. Yay me. And that's how I pushed the box. I compressed the spring, and then I extended the spring, boom, the box moved. So, yeah. But notice, now that I'm in the system, the total mechanical energy of the system did not change. So, the whole point of this progression of examples is to show this. When I'm conceptually thinking about conservation of energy, not when I'm doing the examples we're about to do. Those are easy. When I'm conceptually thinking about it, I have to pay attention to the system. What's in it? What's not? What can do outside forces? What can't? All right? So, there's that. One last thing I would like to mention, if I start moving with the box, so this scenario so far has just been I push the box while standing still. I'm cool with that being TME constant. If if I start moving with the box, so I'm like actively pushing the box, then it's hard to say that the total mechanical energy of that system is constant. Because what's making me move? I'm making the box move. I agree that there's potential energy stored in me. I can make the box move. But what's making me move? Friction with the ground. Well, ground, right? The ground is making me move. So unless I include the ground in this system, if I start pushing the box with the box, like if I go with it, then total mechanical energy can't stay the same, right? Because the ground is having to do positive work on me to get me to move. I'm cool with it if I just stand there and push it, turning my potential into its kinetic. But if I start moving, something had to make my kinetic energy. And that's going to have to be the ground, because that's what applied the force that got me to move. So keep that in mind. Questions about these examples? Okay, so then back to the basics. We have three main types of energy that we're going to include in our system and call total mechanical energy. That has not changed. The first one is kinetic. Kinetic energy is the energy of an object in motion. So it has to be moving to have some kinetic energy. If it's not moving at all, it does not have kinetic energy. Now, I'm going to limit in this particular classroom, not that one over there, right? In this particular classroom, we're talking about object scale things. This set of scissors, right, has no kinetic energy because it's not moving. On a molecular level, all of its individual atoms are moving. It has an average kinetic energy of all of its molecules, and we call that in Miss Sloan's classroom, what? Anybody? Heat, temperature. Temperature. The temperature of this is based on all the tiny little molecules moving around all the time, but the whole of the scissors has no kinetic energy. So just keep that in mind. If you've gotten confused, that's molecular level. I'm talking about whole objects. So, an object has to be in motion. The equation for this, anybody remember? Say it louder and prouder. 1/2 mv squared. So, can kinetic energy be negative? No. Because if velocity is negative, what happens? I squared it. So, this is only positive. It can only be positive. Yay. Very nice. So if we wanted to do an example just to make sure we understand this, right? Let's say this. A car is going 3 times faster than a truck that has 3 times the mass. Which has more kinetic energy?
The car.
The car, why?
Velocity squared.
Velocity squared, right? So even though the truck's 3 times more massive, since the car is going 3 times faster, if you want to see that worked out, 1/2 times 3m times v, that would be the truck, versus 1/2 m times 3v squared. So this is going to work out to be bigger than that. Questions about this? All right. So that's kinetic energy, one of our 3 options. The next one is gravitational potential, which I don't say all of those words very often because it's a lot to write out. Gravitational potential energy. What do I need in my system in order to have gravitational potential energy? The Earth. The Earth. Need Earth in the system. I'll say this. That's 99.9% true. There is a scenario where they say, and this is a satellite orbiting Saturn. So what do I need in that system for the satellite to have gravitational potential energy? Saturn. They could also say this is the scenario of Saturn orbiting the sun. So for Saturn to have gravitational potential energy, what do I need in my system? The sun. Okay, I need that large mass that's actually causing a gravitational attraction. For us and all the objects on Earth, which is 99% of the time what we're talking about, that is Earth. But just know it could be different. Just don't lock yourself in there. What's the equation for gravitational potential energy? mgh. Now this is a height above or below a reference point. That's really, really important. You decide what that reference point is. So could gravitational potential energy be negative? Absolutely it could. Last year I lived up on the second floor. By lived, I mean taught. I taught up on the second floor, and I said that second floor was ground zero. That is what I call my y is equal to 0. So in that case, all of our gravitational potential energies right now would be negative, right? If I call the second floor a height of 0, we are all at a negative height of -3 meters. And so all of us have negative gravitational potential energy. That's perfectly fine. If you got to a question like this, there's a roller coaster and it does this. That's the roller coaster. You could decide that the 0 height is right here. That's 0. And so some of the time on the roller coaster, I would have positive GPE. Some of the time on the roller coaster, I'd have negative GPE. It's fine. Doesn't matter. It's up to you. If it were me, I'd probably set the bottom of 0, but everybody can do what they want. It's a nice thing about life. Questions about gravitational potential energy? Yeah?
If your GPE was like negative and your kinetic energy was positive, you'd still, like, the total mechanical energy would be positive because you take.
Well, it would, technically, I mean, it depends on how big those two things are. I could have a total mechanical energy that's negative. Yeah. But that's only because of gravitational potential energy and that being negative. So you would have to set your reference point to make it happen that way. And I just, in a question, am not going to choose to do that, you know? Because our last, I'll do it in green, I think that's better. Our last type of energy that we're going to have is elastic potential energy. So what am I going to need in my system to have elastic potential energy? A spring. Yeah, I'm going to need a spring. If I don't have a spring, there's no elastic potential. I haven't seen AP do this, but I know that one of my textbooks over here really likes to throw biology references into the physics textbook. Like, that's their favorite thing to do. They're like, if we can put some biology in this, then people will like it better. I don't know. But they will a lot of times throw in that, like, there are mechanical body parts that can be springs, so muscles and things. I haven't seen AP ever do that, but don't be shocked if they say a bungee cord, like bungee jumping, a bungee cord can act as a spring, or that other objects act as springs that aren't just a standard actual spring, right? So just keep an eye out for that if they say in the question, and this is going to act like a spring, say, okay, yes, now it's a spring. So I need a spring. What's the equation for elastic potential energy? Yeah.
1/2 kx squared.
1/2 K, that's the constant, K constant for the spring, whatever that might be, delta X squared. So, can elastic potential energy be negative? Nope. K is always going to be positive. Delta X could absolutely be negative, but again, it's squared. So this is only positive. All right, let's try a couple of examples, and then I'll leave you guys to the rest of it. One quick example I want to do just to make sure we're all clear on this. Without friction, there are 3 slides at the playground. 3 slides at the playground. It's a super fun playground with 3 slides. There's no friction on any of these slides. This is slide A. This is slide B. And this is slide, oh, I didn't do it different. This is slide C. C might be bad. I wouldn't write on C. I wouldn't let my kid on C, but that's okay. All of these start at a height h above the ground. All right? So, without friction, no friction, which slide is going to leave you with the most kinetic energy at the bottom? Which slide is going to leave you with the most kinetic energy at the bottom? What type of energy do I start with? Gravitational potential. Since there's no friction, is total mechanical energy going to be conserved?
Yes.
Yes. So then, if I start with GP, what am I going to end with? Kinetic. So the question is now, do all of these have the same gravitational potential energy to start with?
Yes.
Yes. So therefore, they will all have the same kinetic energy at the bottom. Okay? Now, I try and help out with this. If you're like, how do I solve these types of energy problems? We talked about how we solve force problems. We draw a free body diagram, write an F-net equation, pick an equation, solve a problem. That's how we do that. For mechanical energy problems, we want to say what is the total mechanical energy before and what is the total mechanical energy at the end. Those are the things that we're focused on. So what you should always be writing is a conservation of energy equation. And I can tell you that on every FRQ I've seen that's energy related, the first point for a derived question comes from, did they write a conservation of energy law? So if I was writing one for this, for any of these, it would be mgh is equal to 1/2 mv squared. This counts as a conservation of energy equation. It gets you a whole point on the test FRQ because you have told me that this starts with gravitational potential. There's no external work done on the system. You didn't add any work here. And then it ends with kinetic. This is a conservation of energy equation. And every time I start a problem in the energy unit, I should think about how do I write this out? What energies did I have to start? Was there any work done? We'll talk about work next class. And then what did I end with? And so that's how I get the answer to this question. All right, here's the second question. I'm going to try and draw this better than I did first period. They got on to me during first period. Okay, this is a roller coaster. Roller coaster, there are people in it. Their hands are up because they're having a good time. This is a height of h above the ground. This is a height of 1/2 h above the ground. Everything is drawn to scale. So what I want to know, talk with your neighbors about this for a second. I want to know what height does my roller coaster car get to once it flies off the track? So this is going to end in death and destruction. I can guarantee that. That one I can guarantee. Death and destruction will happen. But what height will this roller coaster car get to before, like at the end? It's going to launch off of here. How high is it going to go? That's the question. Discuss in your group, make a guess.
Why?
There's no friction. There's no friction. All right, raise your hand if you think that it's going to get to a height, total height of h. So another 1/2 h on top of that.
Wait. I have a question.
Yeah.
What's the top of the loop?
2h.
Oh, okay.
So again, raise your hand if you think it's going to get all the way to the end of this thing and make it to a height of h. Well, there are less hands now. The answer is it never makes it off the ramp. Because what happens right around here?
He dies?
Dies, yeah, dying. I promised death and destruction. I wasn't joking. There will be death and destruction. Falls off of the roller coaster. Somebody in second period was like, what if it stayed on and just rolled back down? Couldn't it safely roll back down? I was like, not in my example. It just dies. That's the thing that happens. Yeah, so this circle loop is too high. So it will never, I don't care what the answer is to this because it's never going to get here. Once it gets to this part of the loop, it can't keep going up the loop. So either safely it will roll back down up to there and then do that forever and ever and ever. Or it falls off of it, all the people fall out and they all, boom, crash, thing there. One of those two things will happen. All right? But this is a sneaky one that they will absolutely do on a test to you guys. They'll be like, and what will be the height over here? And you'll be like, aha, it's obviously MGH equals MGH. That would be the conservation of energy equation. Aha, but it couldn't get there, right? It runs out of energy and can't get there. Actually, just to clarify, it probably wouldn't even make it here. Depends on how the loop is, because what happens before it gets to a velocity of 0, which happens here? Eventually, its velocity is so slow that the centripetal acceleration is too low, and it'll... Depends on how the loop is. Depends. But that could happen first, before we run out of energy. All right, last example. These are my favorite type of roller coasters. Absolutely 100% my favorite type of roller coasters. They are spring-loaded. So spring-loaded roller coasters that look like this. So that means at this end there is a spring. The roller coaster cars are lined up against the spring. They're pushed back so they can press this spring. And then they launch going this way. I'll tell you that this guy is 20 meters tall. It's not a super crazy roller coaster. It's a reasonable roller coaster. That's only going 60 feet high. You'll be fine. So if I tell you that this spring's K constant is 20,000 newtons per meter. 20,000 newtons per meter. I have two questions. Question number 1, how much is the spring compressed? How much is the spring compressed? We're making the assumption that this roller coaster can get to the top of this hill with 0 velocity. It can make it to the top of the hill, but that's it. It can get all the way up there, but that's the max it can do. It has no velocity when it gets to the top of this hill. That's the first question, how much is the spring compressed? The second question is how fast is it going right after launch? So those are the two questions. I'm giving you 5 minutes with your teams. Write out a conservation of energy equation. That's your starting point. For the first question, write out a conservation of energy. What energy do I start with? What energy do I end with at the top of that hill? Then think about all the things that you know and solve a problem. Oh yeah, you do need mass. It's 1,000. Sorry, I forgot that. It is 1,000 kilograms total for both of these guys. Total. You do need the mass. It is 1,000 kilograms with all the people in it.
What did we say it's going to end at the top of the hill?
Well, it gets to a velocity of 0 at the top of it.
So,
Yeah.
Divided by 20,000.
That is
That's 196. That's how much X is.
That's about 4.
You can do that. Yeah. And then the square root of that. So this you don't have enough information for, right? You don't know delta x, and you don't know velocity right here. So this is the first transfer of energy that happens. From spring to kinetic. Then I go up to 10,000. The next thing I set this equal to. Right? So I don't have gravitational support yet, but I
This is 10,000. So I say take this out, and this will be
It's not right. I just calculator decimal. Remember, we're scientists, we have to communicate the numbers. People outside this room, when you say root 5, are gonna get scared, they're gonna run and hide. There you go. That's a number they won't run and be scared of. I'm not saying simplified radicals isn't fun.
Can you good?
So I would still just use the MGH. Yeah, because we know that the MGH is equal to all of the energies, but that way I don't have to use the yucky equation for you can use it, you'll still get the right answer, both are correct, but I always choose to use gravitational.
No, that makes sense. Because we use
All right. So my conservation of mass equation for the first question, the thing that I know through this whole thing is that I turn spring potential into kinetic into all gravitational potential. So to answer the first part, I don't have enough information for kinetic energy, but I can set up a conservation equation that says 1/2 k delta x squared equals mgh. Setting the bottom of the track as 0 and plugging in what I know, I get that delta x is what? 4.42. 43. That's actually a lot. Obviously, my spring constant is very, very low because the speed we're about to get is not ridiculous for these types of roller coasters. And the rock and roller coaster at Disney World only actually backs up about like 2 feet, not 12 feet. So that spring must be really, really, really going. All right, for the second one, I now know both the spring potential and the gravitational potential, and I'm looking for velocity, which will be in the kinetic. So when I write out this conservation law, I could have done it 2 ways. I could have said 1/2 mv squared equals mgh. That's probably the way I'm going to do it. I know the energy is the same right after it's launched, when it's on the spring, and at the top of the hill. So all of those energies are the same. So it doesn't matter which one I use. But you can also solve it using 1/2 mv squared equals 1/2 k delta x squared. Either of those conservation of energy equations would work. Either way you do that, you get a velocity of what? No. 19.8. Anybody know what that is in miles per hour? Yeah. It's 40.